And let's go. So today we have another paper. This is a mechanics paper and we're looking at October-November of 2023, paper 4.2, and this is for mechanics. I am just going to dive right in. So, question number 1. A block of mass 15 kg slides down a slope that is inclined. Okay, so this is 15 kgs or 115 newtons, slides down a slope. The top of the plane is at a vertical height of 1.6 meters above the level of the bottom of the plane. The speed of the block at the top of the plane is 2 meters per second, and the speed of the block at the bottom is 4 meters per second. Okay, it's going down, so we'll take down as positive. Find the work done against the resistance to the motion of the block. Okay, so work done is the key word there means that we're talking about energy over here. So I'm going to solve this with energy. You could also do forces, but then you would need to know, you could also do it with the forces. You need the length of the heel and forces. I'm just going to dive in and do it immediately with energy. So when I'm looking at energy, I always check for potential energy, kinetic energy, work done by a driving force, and work done by friction. So in this case, and then what we're going to do is we're going to go from the beginning to the end. So the top of the heel is the beginning and the end is at the bottom of the heel. So in this case, potential energy is changing because it changes in vertical height from the top to the bottom. Our kinetic energy is also changing because it's going from 2 meters per second to 4 meters per second. Okay, there's no work done by a driving force. So there's no engine in this thing. There's nothing pulling it. All right? And so the weight component here will be included in the potential energy. So you don't have to worry about that. And then friction, let's just see. Oh, it's not going to be a smooth slope because they want to know what is the work done against resistive forces. Okay, so if I look at my energy before, it must be equal to my energy after because energy is conserved. Okay, so in the beginning, I have the potential energy of the block when it's up at the top of the hill. And I've also got some kinetic energy. And that's all that I've got. And then where is the energy going? So the potential energy is going to be completely depleted. There's none left. But there is some kinetic energy, some final kinetic energy. And all the rest of the energy needs to go to overcoming friction. Okay, so here we've got our mgh is half mv squared. So I'm just writing out my formula. I'm going to leave this as work done because they're asking for work done. They're not asking for the frictional force or the length or anything. Okay, our mass of our block is 15 kgs. Gravity is just 10. Our vertical height is 1.6. I just want to see, they do give us the vertical height, so not the slope. That's important. Our mass is 15, and our velocity is then 2 squared. That's what's happening in the beginning. And then at the end, we've got a half times 15 times 4 squared. And the only unknown in this case is the work done against friction. So I'm just going to take all my other terms to the other side. So I've got 15 times 10 times 1.6, 0.5 times 15 times 2 squared, and then minus 0.5 times 15 times 4 squared. And my work done is then 150 joules. Right, so that's a nice straightforward energy question, and that's the whole of question 1. Okay, now we jump into question 2. As soon as I see a ring, okay, so a ring needs to ring some bells in your head. Okay, whenever I see a ring, I know that the tension in my rope is going to be the same. So whatever the tension is on the one side, it's going to be the same as the other side because it goes through the ring, and you can't have one side of the rope pulling more than the other. Okay, so that's the first trick to do with a ring. I can also see that here I've got like a wall or something. So if I were to draw a free body diagram, I would want to get rid of my wall. So right now I'm just going to erase it. Technically, you should probably actually just redraw the diagram, but that's what you want to do. Okay, so maybe I will redraw it. Okay. And then the other thing that I'm just noticing here before I've even read the question is that you've got a mass. So this is going to be m kgs hanging down, so it's 10m. Right. Let's actually read the question. So the diagram shows a smooth ring R of mass m kgs threaded on a light inextendable string. A horizontal force of 2 newtons acts on R, so we can see that. The ends of the string are attached to a fixed point A and B on the wall. Part A, R, makes an angle of 30 degrees, and then B, R, 40. With the vertical, the string is taut. The ring is in equilibrium. Okay, so there we also know some of the forces in the x direction are 0, and some of the forces in the y direction are 0. Find the tension in the string and find the value of m. Okay, so I'm just going to draw a free body diagram here on the side. So that's 2 Newton. Down we've got 10m, that's what the force would be. Then we've got our tension in the string, and if we look at our alternate angles, that's going to be an angle of 40 over there. And then here we've also got the tension in the string and an angle of 30. Okay, and our strategy for equilibrium, sum of my forces in the x direction must be equal to 0. So I am going to just start doing that. So I've got minus t. Okay, my angles are in funny places. So in this case, it's sine 30 minus t sine 40 degrees plus 2 is equal to 0. Okay, and so if I were to take my t's to the other side, plus t sine 40, what I'm going to do is I made a video where I didn't keep the degrees. I just calculated my decimals. In this one, I'm going to actually just keep my degrees. So can you see I've factored out a t? So if I were to make t the subject of the formula, it would be over sine 30 plus sine 40. Now, don't let these ratios confuse you. That is actually just a numerical value that I can easily find on my calculator. I'm just not doing it right now because I want to, I guess, practice doing this with all my decimals. Okay. Now, let's go. So that was the sum of my forces in my x. Now, the sum of my forces in my y direction is also 0. So if I look at my y direction, I've got t, and now we're looking at cos 30 minus t cos 40. Then I've also got my 10m going down, and then my 2 doesn't have any component in the y direction. So if I were to make t the subject of the formula, I've got cos 30 minus cos 40, and that is equal to 10m. Okay, so if I look at t, I've got 10m cos 40. Okay, so I have got t as the subject of my formula in both of these, so I can equate them to each other. And that's equal to 10m, and that's over cos 30 minus cos of 40. So I can then calculate my m. I'm going to now do all my degrees. So I'm saying 2 divided by, we've got to make sure the calculator is in the right mode. Okay, 2 divided by sine 30 plus sine 40. And then we're going to multiply it by cos 30 minus cos 40. And all of that should then be divided by 10. and we then get a value for M. And in this case, my M is 0.0175 kgs. And then if I look at my T value, I'm going to say 10 times my answer divided by cos 30 minus cos 40. And that gives me an answer of 1.75 Newton. Okay, so the tricks in this question were just the ring, drawing a free body diagram, making sure you add the weight, and then we do our normal strategy of sum of forces in the x and y direction is equal to 0. Okay, let's jump into question 3. So, a block of mass 10 kgs. Okay, you can immediately, when you see these things, you know going down the slope is mg sine of 30, and then my y component is going to be mg cos of 30. When I look at this, I immediately see I've got another angle, well, another force pulling on this, and it's got a component in the y direction. So my R value is not just going to be opposite the weight. It needs to be the resultant of these two. So the 120 degrees is lifting it up a bit. Okay, so it's going to reduce my R. Okay, so just take notes before we even start the question, just take notes of these things. So a block of 10 kgs is at rest on a rough plane. Okay, so we've got to add friction. 30 degrees, a force of 120 Newton is applied to the block at an angle of 20 degrees up the slope. There's a resistance force, a force resisting the motion of the block, and 200 joules of work done against this force when the block is moved 5 meters. Okay, so we need to remember, how do we connect joules to force? So our work done is our force, and then it must be parallel to our distance. There's a force resisting the motion of the block. 200 joules of work done against this block. So that's frictional force when it's moved 5 meters up the plane. Okay, so friction is acting down the plane. Okay, so we can work out what is our frictional force because it used 200 joules in 5 meters. So 200 divided by 5 is a frictional force of 40 newtons. Okay, so right, now the speed of the block when it has moved, find the speed of the block when it has moved a distance of 5 meters up the plane from rest. Okay, so this thing is not in equilibrium. If it's not in equilibrium, that means it's going to be accelerating. So we need to figure out what's the acceleration. How do we do that? We can look at the sum of the forces is mass times acceleration, and I'm going to look in my line of motion. So if I look at all the forces in my line of motion, that's up the plane, what have I got? I've got minus my mass component, minus mg sine 30. I've got my friction acting down, and then I've got 120 cos of 20 acting up. And that is going to give me my resultant force acting up, which is then equal to MA. Okay, so I'm just going to fill in all my blanks. So minus 100 sine 30. That's 10 kgs and A, so we should be able to do this directly. And divided by 10, I'm getting an answer of 2.27. That's my acceleration. 2.276 meters per second squared. I'm actually going to just save that value into my calculator so I can use the entire value when I'm doing this. Now I'm going to just jump into Subat because we are starting from rest. We are traveling 5 meters. we are accelerating at 2.276 meters per second squared, and they want to know what's final speed of the block. So we can take our equations of motion, which are on our MF19. Here we've got 0 squared plus 2 times 5 times our acceleration. I wrote those actually the wrong way around. And remember to square roots. And I am getting an answer here of 4.77 meters per second. Okay, and that is the whole of this question. So they didn't actually ask us about that R value, which I find quite interesting. Right, but that's not a problem. That was 5 marks. Okay, jumping right into the next question. A particle of mass 0.2 kgs lies at rest on a rough horizontal plane. Okay, that was really important information. I almost left out. Okay, a horizontal force of 1.2 newtons is applied to P. Okay, so whether it's pushing it or pulling it, okay, it's 1.2 newton, it'll have the same effect. It is given that P is in equilibrium. Find the coefficient of friction between P and the plane. Okay, so it's not saying it's in limiting equilibrium, it's just in equilibrium. So our frictional force is going to be opposing it. Friction is mu times R. In this case, we've just got our R, the resultant of the forces in the y direction is just going to be opposite the weight. So my frictional force is 1.2, and then I've got mu, and my R value is going to be 0.2 times 10. And I am getting a mu value of 0.6. Okay, so what I'm noticing here, I find this an interesting question. It's straightforward, but I've noted that, oh, it is in limiting equilibrium. Okay, it's in limiting equilibrium, so this is now the mu of this material. Okay, given instead that the coefficient of friction between P and the plane is 0.3. Okay, so the coefficient of friction is less. That means this particle is going to be moving. Find the distance traveled by P in the third second of its motion. Okay, so it's going from 0 to 1, 1 to 2, and from 2 to 3. How far did it move? Okay, right, so now we know it's been pulled forward by 1.2, but it's not going to be able to resist as much. Okay, so we know it's 0.3, and then our R stays the same, which is just 20. So our frictional force, I shouldn't say 20, that doesn't make sense. 2, our frictional force is 2. Okay, if it was 20, you would see this particle would be going backwards, which doesn't make any sense. 0.3 times 2, because frictional force only resists a force. It doesn't have, it's not pulling it. Okay, anyway, 0.6. So now we can work out our acceleration. So it's going 1.2 forward, 0.6 back. It has a mass of 0.2, and we can see what is our acceleration. Minus 0.6 divided by 0.2 is 3. Okay, so I think, so the acceleration is 3 meters per second squared. Now, I'm just going to look at an equation of motion. So if I'm starting from rest, okay, we don't know what the distance is, but maybe I can find a formula for distance. We can also find a formula for time because we're going to be relating time and distance here. And I've got my acceleration. Okay, because it's accelerating at a constant rate, I can use Suvat's. And I can write up a formula between these 4 things. So S is equal to UT plus a half AT squared. Okay, now if I want to know how far has it gone in the third second, so this is T1 to T2, T3. I'm going to plug in T is 3, and that's going to be a half times 3 squared. And that is a half of, I should have known that as well, but anyway. And then if it's T2, if T was 2, it's a half times 2. No, a half times 3. This is 6. Okay, so in its second, it's 6, displacement of 6, and in the third second, it's a displacement of 13.5. So how much did it travel in the third second? 13.5 minus 6 gives us 7.5 meters. Okay, pretty interesting question. Make sure that you read your questions very carefully. Okay, each and every keyword means something. So here, you could easily have read how far does it travel in 3 seconds. Okay, it's not in 3 seconds, it's in the third second. Okay, next. And then the other thing is also just to count. Okay, if it goes from 0 to 1, that's the first second. 1 to 2 is the second second. 2 to 3 is the third second. Okay, it's not silly if you do that. Like, I take my time to just figure out exactly what I'm doing. Okay, now, next question. A particle of mass 0.5 kgs is projected vertically upwards from the ground at the speed of 25 meters per second. Okay, so projectile motion. It's going up, it's from the ground. Our u is 25 meters per second. Find the speed of A when it reaches a height of 20 meters. Okay, so we don't know where it is. We want to find the speed at that point though. We know it's 20 meters above the ground, sorry. We do know where it is. Acceleration is minus 10 because we're working with gravity. Okay, and we want to know our final velocity. So v squared is u squared, it's 2as. Okay, I always draw an arrow to say where I'm going from, and it shows my direction that I'm taking to be positive. Okay, so here we've got 25 squared, 2 times minus 10 times 20, and that's 2 to 5, and the root of that is 15. Okay, when A reaches a height of 20, okay, so now we know it's got a speed of 15 and it's reached a height of 20. It collides with particle B. Okay, that was really nice of them to make us like figure out what speed it's going to collide with. Okay, so when it reaches a height of 20 over here, it is colliding with particle B of mass 0.3 kgs, which is moving downwards in the same vertical line, and it's given us a nice speed of 32.5. That's really kind of them. Okay, 32.5. In the collision between the two particles, B is brought to instantaneous rest. Show that the velocity of A immediately is that downwards. Okay, so we can now decide, whenever you're doing momentum, you have to decide whether up or down is positive. So I'm just going to say down is positive, because they wanted us to show that it's 4.5 downwards. Okay, my momentum is conserved. Okay, so I write down my momentum formula, and now I'm just going to go AB, AB. I should have probably just said MA, UA, but anyway. Right, my mass of A is 0.5. Just filling that in. My initial speed of A, so we know that it was 15, but it was 15 going up. So we must make it now negative 15. Okay, and the mass of B is 0.3. And B was coming down at 32.5. Okay, then A we are trying to show that the velocity of A, so we want to show what is the velocity of A after the collision, and we know that B came to instantaneous rest, so that's 0. Okay, so this whole term kind of falls away, and I just need to solve for V. And I've got all my ups is positive, and my downs is, no, my ups is negative, my downs are positive, so my sign convention should be correct. Doesn't matter which one you do, so long as you stick to your correct convention. Okay, and I get a velocity of 4.5, which is exactly what they wanted me to prove. Okay, let's jump into the next question. It looks like an interesting one. Find the time interval between A and B reaching the ground. You should assume that A does not bounce when it reaches the ground. Find the time interval between A and B. Okay, so we just got to figure out what is happening. These two things collided at 20 meters. Okay, they collided. After the collision, B was at instantaneous rest. So it's going to be 0 meters per second. Our acceleration is still minus 10. No, I'm just going to take down as positive, so I'm going to say it's 10. We want to know what time it reached the ground, and we know that it's moving 20 meters per second down. So I'm just going to figure out what's happening to B first. Okay, so it starts at rest, so we've just got a half times 10 times d squared, and that has to go a distance of 20. So 20 times 2 divided by 10, and then I have to square root it. So B reaches the ground after 2 seconds. Okay, now what was happening with A? We had to prove that A has a velocity going downwards. So B like knocked A a little bit down. So 4.5. So A is also going down. So for particle A, our initial speed is 4.5 meters per second down. Our acceleration is 10 going down. We don't know the time, and our distance is also 20. Okay, so S is ut plus a half at squared. And here, oh, that's not 0, so we've got 4.5 times our time, a half times 10, 20. Okay, here we're going to have to solve a quadratic. Okay, so 5t squared plus 4.5t minus 20 is equal to 0. You could put this in a quadratic formula, and you will get 2 answers for t. Okay, our first answer is 1.6, and then our other answer is going to be a negative answer, and we're not looking at that one because we don't look at negative time. So our time is 1.6. So A reaches the ground 1.6 seconds after the collision, and B reaches the ground 2 seconds after the collision. So difference in time is going to be 0.4 seconds. So just the one minus the other one. All right. Let's jump into question 6. Okay, so we've got 2 questions. 2 questions left. Okay. A railway engine has a mass of that, and it's towing a coach. Okay, so we've got the engine and the coach up a track, inclined. Okay, so I just wanted to know before I draw anything, where we're going up or not. Okay, so 120,000 kgs. Big note to myself, watch out for all the zeros, because now I'm also going to have to turn this probably into weight. Okay, and 60,000 kgs. Okay, upper track inclined at an angle of alpha. They do give us alpha. 0,02. Okay, there is a light rigid coupling parallel to the track, connecting the engine and the coach. Okay, this is already looking interesting. So now we've got a coupling, and it's light and rigid. The driving force produced by the engine, driving force, is 125,000 Newton. And there's a constant resistance to motion on the engine. So let's put that in red. 22,000 on the engine and 13,000 on the coach. Okay, make sure that you've got all the zeros. Make sure that you've got the right friction on the right object. Okay, I have gotten that wrong before. Okay, find the acceleration of the engine and find the tension in the coupling. Okay, so don't worry about a coupling. This is just a connected particle question. Okay, find the acceleration of the engine and then the tension in the coupling. Okay, so what I'm going to do, I'm going to use my system. This is a new thing. I used to always split up my particles and look at them separately, but I'm going to now just look at the system as a whole. Okay, what you need to know there is if you're looking at the system as a whole, you can kind of eliminate the tension forces initially. Okay, so I'm looking at my whole system. What are all the external forces acting on this thing? I've got my mg sine theta, m times 10 times sine alpha. So that's acting on the coach. And then I've also got my 120,000 times 10 sine alpha. Okay, so those my masses are acting down. And I've got my 13000 and I've got my 22000 all acting down. The only thing acting up is my driving force. Okay, so sum of my forces is mass times acceleration. Because I'm looking at the total system, I've got to look at the total mass. So my sine alpha is 0.02. So minus that, minus my frictional force, minus my other frictional force, plus my driving force. And all of that is equal to my mass, so it's my combined mass, times acceleration. Okay, so that's a lot of summing going on there. I should have probably just done it all in one line. But make sure you're typing in everything correctly. So 60,000 and another 0 times 0.02. I'm maybe just going to write each of these. I don't know why I rewrote all of those. Anyway, put it all in one line, and that is equal to 60,000 plus 120,000. Okay, so now I can just add them all up. Watch that you are doing the right thing on your calculator. There's no point in getting everything right and then just typing stuff in incorrectly. Okay, so here I get an acceleration of 3/10 or 0.3. Okay, so find the acceleration, and then they also want the tension in the coupling. Okay, so here we can just, we're going to have to split up the particles because we want to look at the tension in the coupling. So I might just take my coach I've got my weight going down, I've got my friction going down, and I've got my tension going up. Okay. So always draw the free body diagram. That's like tip number 1. Tension is going up. Direction of motion should also be positive. Tension minus. And then my mass, now we're only looking at the mass of the coach, 60,000. And we already know our acceleration is 0.3. So our only unknown is the t. Okay, plus 13,000 plus 60,000 plus an extra 0. 1, 2. So I am getting a tension of 43,000 Newton. Okay, so the principles of these connected particle questions are all actually quite similar. So just try and practice them whether you're either splitting them up or you're working as a system. Okay, at the instant when the engine is traveling at 30 meters per second, so they're giving me an instant in time, so this is going to be a power question. Okay, it comes to a section of the track inclined upwards at angle B. Okay, so we were going at angle alpha, now we're going at angle beta. It doesn't matter. So we were going at alpha, now we're going at beta. It just always goes according to the horizontal. The power produced by the engine is 4,500,000 watt. Whenever I see power, I've got 2 equations. My driving force times my velocity, or my work done divided by time. Okay, they've given me velocity, so I'm assuming I'm using this formula. The power produced, and as a result, the engine maintains a constant speed. Okay, that's nice. Okay, assuming that the resistant forces remain unchanged, find the value of beta. Okay, so let's just work out one thing at a time. First of all, I'm going to look at my driving force, because I've got power. My driving force times my velocity of 30. So what is my driving force? Okay, you would expect it to be a big force, 150,000 Newton. Okay, I'm just going to actually erase the first part of my picture. Nothing's changed. All I know is the angle's not different. It might be higher and it might be lower, by the way. Okay, I've got now 150,000 Newton pulling upwards. And this is at a constant velocity. Okay, so that means everything pulling backwards is going to equal everything going forwards. Okay, so I'm just going to write down my weight component minus 60,000 times 10, and in this case it's now sine beta. Okay, so those are my 2 weight components, my frictional component, my other frictional component. Okay, and the only thing going up is my driving force, and these things must equal to 0 because it's going at a constant speed. Okay, now the only unknown is my beta. Okay, so let's get all the terms with beta can go on the one side, everything else goes on the other side. So 60,000 times 10 plus 120. Okay, so on my one side of the equation, I've added up my sine betas, and then I'm keeping, so I've taken those to the right, I'm going to keep these on the left. It's minus 13,000 minus 22. Okay, that's 115,000. So now divided by 1,800,000. Okay, really strange. What do I eventually get this as? Beta is now 3.66. And they always say a round of degrees to one decimal place. So 3.7 degrees. Cool. Let's just quickly look. Is that now steeper or less steep? So sine of 0.02 was an angle of 1.145. So it is steeper. Okay. Cool. Nice. That was an interesting question. I actually quite like that. So every keyword makes sense. Well, every keyword is super important in these questions. Okay. I'm going to try and go as fast as possible with the last question. A particle x travels in a straight line. The velocity x at time t of traveling is given by that. So they've given us a velocity formula and it's curvy. Okay, so we're working with kinematics, but we're going to have to integrate and differentiate. The acceleration of x is 0 at t is equal to p and t is equal to q. P is less than q. All right, so what they're trying to say, when the acceleration is 0, that means the derivative is 0. So there's a turning point at p and at q. Okay, find the value of p and q. Okay, so yeah, we go SVA, to go down the chain, we have to differentiate. And to go up, we integrate. Okay, so if I've got velocity, I can differentiate that. 0.8 times 2 is not 3.6t. My 5.6 falls away. Okay, no, but I've still got a minus 6. Okay, there's 4 terms, so just watch that you get them all. That's now equal to 0, so where my derivative is equal to 0, that is where the acceleration is 0. Okay, I'm going to divide everything by minus 0.3. Just because I don't like the minuses and I don't like the fractions. Okay, so now we can easily solve for this. I'm seeing 10 and 2. Okay, so 1 is 10 and 1 is 2, so it's the smaller one. P must be equal to 2 and Q must be equal to 10 because P is less than Q. Okay, so that's quite simple, but you do have to understand how the graphs work in terms of differentiating. Okay, it is given that the velocity of x is 0 at t is equal to 14. The velocity of x is 0 when t is 14. Okay, so if I plug in 14, I should be getting 0 as my answer. Find the velocities of x at that and that, and hence sketch the velocity time graph. Okay, so but they're basically giving me a time point for when the time is 14. Let's plug in 2, so my velocity at 2. Okay, what is that? Okay, that is equal to 0. And my velocity at 10 is minus 12.1 times 10 to the power 3. that is a velocity of 25.6. Okay, so, and hence sketch the velocity time graph. Okay, let's see if we can plot this. Okay, so when my time is naught, I'm going to have 5.6. When my time is naught, okay, then when my time is 2, so 1, 2, my velocity is naught, okay, and there's a turning point there because acceleration is naught there. Then 1, 2, 3, 6, 8, 9, 10. And then 14, they said at 14 it's 0. So, and at 10, there's a turning point somewhere at 10. And that's where my velocity is 25.6. So I'm going to assume that's a maximum, that's a minimum. Okay, so I'm going to draw this and it's going to come down there. So it's going to look something like that. This is a terribly drawn graph, so we should probably just make it a little bit nicer. The point is it's crossing the x-axis at specific places, not the x-axis, the time axis. Okay, find the total distance traveled between t is equal to 0 and t is equal to 15. Okay, so we must just check what's happening. If that's under the graph there, we've got to add that little part as well because they want the distance. Okay, so what I can see here is I can integrate all the way from 0 to 14. Okay, because that is all above the line. And then I'm going to have to go between 14 and 15, but use the mod of that. Okay. Okay, so I'm just getting my equation. I'm just going to do one part at a time. I'm not going to do the other one for now. Okay. So the important parts here when you're looking at integrating is you've got to know where it cuts the x-axis, and that's why they made us draw this drawing. Okay. So I'm going upper power divided by the new power. So this is 14 to the power 4. Okay, if I subtract all those terms, it's going to be 0. 1.8 over 3 to the power 3. 3 times 14 squared plus 5.6 times 14. Okay, that's going to give me 176.4 meters. So that's for the first 14 seconds. Okay. And if I'm doing the last second, I'm just going between 15 and 14. And I'm not going to do the whole thing. I'm just going to plug in my values. Minus 0.1 over 4 times 15. 3, 15 squared plus 5.6 times 15. All of that minus 176.4, because I'm going to plug in 14 again. I already have that answer. So that's quite a cool trick. Divided by 4. Okay, I'm noticing that I am not typing this in properly. Okay, times 15 to the power 4 plus 1.8 over 3 over 3 Cool, so I'm getting a value, and then I'm saying minus 176.4. That's what I got from above. I expect this answer to be negative because it's underneath my graph. So now I've got to make it positive. And that comes because of the word distance. Okay. So my final answer is 184,425. I'm going to use all of my numbers because it's an exact value. It stops, so I'm going to use that exactly. Okay, and that is the whole paper. So really, I really find if you know your theory, if you know your notes, you're going to be okay with these types of papers. Anyway, give me your feedback. I don't think this one was too difficult, but you need to know why they're asking you to do specific things. So for example, here, you need to understand your turning points. You need to understand what the graph looks like, the fact that you can integrate all the way from 0 to 14, and then underneath the graph, you've got to add that part. Anyway, I hope that this was helpful, and all the best for your coming up exam.